We're going to go ahead and take a look at finding limits. We're going to look at a graphical approach to finding limits and a numeric approach. And then we will be looking at a symbolic approach. Limit is basically what is your function getting close to as you get closer and closer to a particular value for x. We have the notation limit as x approaches a of f of x is L, which means the limit of f as x approaches a is L. Basically, as you get closer and closer to a particular value of a for your x value, what does your function get closer and closer to? And if it's getting closer and closer to one particular number, then that's what our limit is that we're discussing and looking at. So let's go ahead and investigate the function of x cubed minus 1 over x minus 1. We know we can't have x being 1 because we would end up dividing by 0. Well, we're going to go ahead and take a look at this limit. Your limit as x approaches 1 of this function in 3 different ways. Because we know we can't use 1, but what happens when you get close to 1, either from the right side or the left side? Well, if you look at the graphical approach, if you just go ahead and graph it, you get this right here. But it has a hole right here when x is 1. You'll notice on each side of your hole, as you get closer and closer to 1, your output gets closer and closer to a height of 3. So limits can be investigated graphically. Limits can also be investigated numerically. The easiest way to do that is typically with the table feature on your calculator. You put your function still into your y equals. Using your table feature, then you go ahead and you start typing in values for x that are closer and closer and closer to 1. And you notice as we come in from just below 1 and get closer to 1, that the outputs get closer and closer to the value of 3. You can also try numbers slightly above 1 and come back down closer and closer to 1, and that's what we're doing here on the right side. And you'll notice those values, as x gets closer and closer to 1, your y values get closer and closer to that 3. So graphically and symbolic or numerically, we would say our limit is 3. We can also look at this symbolically or algebraically. What we're going to do is we're going to just work with the function itself. You'll notice the top ends up being differences of cubes because it's an x cubed minus a 1 cubed. So if you factor that according to differences of cubes, we end up getting this here. Well, you'll notice then that your x minus 1 drops out on the top and the bottom. And so then you're just left with this quadratic. So now we don't have to be concerned about going ahead and plugging in 1 here. We couldn't plug in 1 initially because we'd be dividing by 0, but we eliminated that factor that caused the problem. So now all we have to do is come along and plug in 1 for our x's. Plug in 1 for our x's, add everything together, and we get a limit of 3. Well, we can go ahead and investigate most functions in all 3 of these ways. Here we're wondering what happens as x gets close to 0 of x over root of x plus 1, all minus 1. We can investigate that in 3 ways. We could put that into our y equals and we could graph it and see what happens. Well, when we put that into our y equals and graph it, we end up getting a graph that looks like this. Now remember, we're wondering what happens as x gets close to 0. Well, here's x being 0. What's your height? And it's 2. So we would say from a numeric point of view, we would have a limit of 2. It may not appear like it on this graph, but there's really a hole right here in your graph at x being 0. Once again, with your function in your y equals, you can go ahead and look at it numerically. You go ahead and you continue to put in numbers closer and closer to 0 for your x values. And when you do that, you'll notice on each side you get closer and closer to 2. So from a table, number-wise, we would say we're having a limit of 2. Well, we can also investigate this problem symbolically. To investigate it symbolically, we need to try to do something with that root. So we're going to rationalize the denominator. To do that, you want to multiply the top and the bottom by the conjugate. Well, multiplying the top, that's pretty easy. It's just x times the whole top. Multiplying the bottom, you're multiplying conjugates together. Remember, the inner and outer terms drop when you multiply conjugates. So you multiply the first terms together, and you get an x plus 1 because the root drops out. And then you multiply your last terms together, and it just gives you a minus 1. You'll notice the bottom does simplify down to just x. So now we have an x on the bottom. On the top, we have an x times the whole top. So those x's drop out. We've now eliminated the issue of having something in the denominator that would cause us to divide by 0. So now we can go ahead and plug in 0 for our x. Then we're going to get the square root of 1, which is 1 plus 1, and so we get 2. So let's continue to talk about limits. Not all functions have limits. Sometimes they will fail at a particular spot. Here's an example of a function of the absolute value of x over x. The graph of it's over here on the right. Hopefully this graph makes sense to you. When you're to the right of 0, you're putting in positive numbers, and while the top is always positive because it's absolute value, and the bottom would be positive, they'd be the same value, both positive, so when you divide, you get a positive 1. So that's why we're always at a height of 1. To the left of 0, over here in the negatives, you're putting in a negative x. Well, the top's going to make it a positive value, but the bottom would be the negative value. Numerically, they'd both be the same size, but one would be positive, one would be negative. So when you divide two numbers that are the same but of opposite signs, you get a negative 1. So we're down here. You'll notice when you come into x being 0 from the right, you're reaching 1. When you come into x being 0 from the left, you're approaching negative 1. Since you're not approaching the same number on each side, we would say your limit does not exist. For your limit to exist, you need to be approaching the same number from the right and from the left. We're not talking about infinity either, because infinity is not a number. It has to approach a particular number. When we're approaching the same number from each side, we say we are converging. If you're converging to the same number on each side, you have a limit. If you are not approaching the same number from each side, or you're approaching infinities, we say we are diverging. So as we take a look over here, we have our 1 over x squared. You'll notice on the graph, when you approach from the left side, you go up towards positive infinity. When you approach from the right side, you go up towards positive infinity. Since you are not approaching one particular number, we would say there is no limit. In this particular case, we would say it's an unbounded behavior. Now, when we're saying our limit as x approaches 0 of 1 over x squared equals positive infinity, we're not saying that your limit exists. We're saying that it really diverges, and then we're describing what happens because it's going towards positive infinity.